So to begin with, let me first talk about what a stencil computation is. A stencil computation is a common pattern that appears in scientific simulation codes and image processing and so on. And it's basically a pattern where you're updating a multidimensional grid of a subset of each point's neighbors. So it's easy to write this in it looks very simple, where a weighted sum of its neighbors. When it's actually turned into code, it becomes quite a bit. That these computations are so important for the current architecture that they're working on. So here's an example. And this has had some loop. Commonly, people will hand vectorize and it's very difficult to optimize for new architectures. Optimized stencil that if you want to optimize, you have to rewrite by hand, and before you do that, the code also makes, because those compilers can't really undo, for example, to this loop. Polyhedral analysis is going to it's just going to try to do the best current structure of the loop. So help mitigate the issues with having level language. Sorry, mitigating issues. So you can write it in a domain-specific language, and all of this work is given a snippet of Stencil that fully describes the algorithm without any optimization. DSL code, it can then be used to generate applied so that a compiler is free to do. So in the rest, and then I'm going to talk about, and then finally we'll do a little bit of evaluation. Imagine this stencil piece and corresponding summary that says what it. How would you go about for this piece of code? Well-known method for reasoning about programming. Actually do this for the set of verification conditions that and those verification conditions amount to a. But in order to the loops in the code, loop invariant for the I loop, and these loop in those properties are more complicated that I'm going to ensure that the loop invariant is valid for each iteration loop condition is no longer valid, that the post in 1969 in Hoare's original paper. To do this kind of proof, we have provided to us. Once we have the invariant conditions and running them through an SMT solver, so in our case, we want to generate those post conditions. And that's what I'm going to talk about next. We use a technique called program synthesis. What it does is that for some program that in our particular case, such that for all program states, so this particular problem in doing so for stencils, we encountered all of the possible post conditions. That search space is so massive that the second problem arises from the presence of post conditions. And so I'm going to talk about these first two things. For synthesis over all possible loop stencil, we try to generate a template of what our post conditions and loop invariants will look like based on the specific instance of the stencil that we have. In order to do that, we use mixed symbolic and concrete evaluation. And in our mixed symbolic and concrete evaluation, we set all of the integer pieces of state to be random small values. Those are concrete values. And we set all of the array entries to be symbolic values. So in this case, for this piece of code, we set B to have symbolic values B0, B1, B2, and so on. And we set the all of the other variables to be small random integers. So then we actually try to execute this symbolically, and we end up with our output array A having entries that are a combination of concrete and symbolic inputs. Based on this, we perform some simple anti-unification to give us a template that says the inner part of our loop invariant here and the inner part of our post condition is going to have this form that looks like Aij depends on 2 points in B that are distinct. So as you can imagine, something like this drastically reduces the search space because now we've just put it down to 2 points in B that are neighbors of the central point in A, as opposed to any arbitrary stencil that could exist. It's also important to note that we're not trying to use anti-unification to figure out which points the output depends on. We're actually going to allow the synthesizer to do that because it's much better suited for that particular search problem. And I should also say that we take a lot of care in generating our post conditions to make sure that they're not trivial. So we're not looking for arbitrary post conditions like true equals true. We're actually looking for a specific kind of postcondition. And that specific kind of postcondition has the structure that for some contiguous space in the output, we want to make sure that each point in that space depends on some function of a neighborhood of points in the input arrays. So that takes care of trying to limit the space when it comes to the template that we're using to generate the postconditions and invariants. The other problem comes about because of the existence of quantifiers within our loop invariants and postconditions. And to show you that, we have to look kind of carefully at the synthesis problem we're trying to solve. If we look inside those verification conditions, as I showed before, there are some requirements that our loop invariants need to have. So for example, one thing that our loop invariant for J needs to have is that if the loop invariant for J is true and the loop condition is true, and the loop condition is no longer true, that implies that the postcondition is true. When you express this as a Boolean formula, that implication just turns into two ors on the left-hand side of negated things, right? This is just the standard way you implement implications in Boolean formulas. But the issue here is that within ij, we also have these universal quantifiers. And when you negate those universal quantifiers, they become existential quantifiers. So what that means is instead of solving this there exists for all problem, which is what synthesis can do, we're trying to solve a problem that is there exists for all there exists, which is quite a bit more complicated than the original problem. The standard approach for this is Skolemization. And if you're familiar with Skolemization, what you do here is that you try to replace that innermost there exists z with a function. And this is based on the observation that if you have something that says for all y there exists z, you can replace that with a function that for each of those y's tells you what that z is. But the problem is that Skolemization in our context is going to result in a very complicated Skolem function. That function is going to have lots of conditionals because based on where you are in the loop, you have to kind of do different things. And trying to figure out exactly what that Skolem function looks like is extremely difficult. So what we do instead is something that we call partial Skolemization. And in this case, we replace that innermost quantifier with a function that is actually going to return a small subset of possibilities. In other words, what we're going to do is have this function that will return, fp of y is either going to be p1 or p2. And then we allow the synthesizer to decide which things should go there because the synthesizer will pick the right things in order to make the whole thing true. This drastically reduces the complexity and is not really undoing the Skolemization, because if you think about what full Skolemization looks like is the ors on the right-hand side have to deal with all of the possible z's, right? And in this case, we're just allowing the synthesizer to pick some z's for us that will make the loop invariant actually work. So a concrete example of what this looks like within a sketch looks something like this. We're using the sketch system, which has a Java-like syntax, and an invariant for J here is going to pick a couple points in J and a couple points in I, and we just let the synthesizer deal with all of that. What we're looking for here is some invariant that will actually make our postcondition true, and while we're doing that, the if statement in the inner loop is really the thing that we're trying to figure out, right? That's telling us what is the stencil actually doing. And therefore, we hide all of the complexity of picking those points in these generators. If you're familiar with Sketch, a generator will just generate a context-specific thing that goes in there. And here we're trying to generate context-specific points as well as context-specific points for Skolemization. So in order to talk a bit about evaluation, I'm going to describe the system that we actually built. The system we built is called Sting, and what we try to do is end-to-end transform arbitrary stencils in Fortran into optimized domain-specific language code. So in order to do that, we have a parser that's built on the Rose framework, which identifies potential fragments that could be stencils. Those code fragments are then passed to a summary searcher, which does the entire process that I just described. We build a template for synthesis. We run that through the sketch system. Once that's synthesized a candidate set of postconditions and invariants, we then pass that to a formal verifier. In our case, we use Z3. And we do that because the sketch system uses bounded reasoning, and we want to ensure that we're not using bounded reasoning and proving that actually this is the correct postcondition and is the correct loop invariance. So once that's been verified, we take that postcondition and we use that to generate backend code. In the paper, we describe two backends. We generate Halide code. Halide is a domain-specific language that was presented at PLDI a couple years ago. We also generate naive C++ that we can then try to use Intel's auto-vectorizer and auto-parallelizer, for example, in order to optimize. Now, our parser takes care of a lot of the gritty work also in integrating the new code into the original code by transforming those loops into function calls with the right parameters to the generated code. Our system does have some limitations. To begin with, we concentrated on a specific subset of all stencil computations. This specific subset is stencils that have no conditionals or boundary conditions. They have distinct input and output arrays, which means we don't have Gauss-Seidel-like stencils or dynamic program-like stencils. And we only deal with incrementing loops. Now, all of these things are not fundamental limitations to our technique. They're just engineering limitations in the sense that we, didn't want to try to build something that was completely general without being able to first prove that it worked for a subset of stencils that happened to be very common. And as you'll see in our evaluation, we were able to find many real-world stencils that, that correspond to this specific subset. There's an additional limitation that even with very careful generation of sketches, the size of the synthesis problem can be so large that the time to solution may take hours or may take so long that we just time out. But this latter limitation is something that has been evolving in the lifetime of our project. So for example, when we first started doing this, even for simple stencils, it used to take 10 hours to synthesize something. But those kinds of stencils now take a matter of seconds because of new optimizations within the sketch system that have better strategies for solving this kind of particular problem. So for benchmarking, we looked at 4 different scientific applications and 2 sets of benchmark codes. All of the benchmarks are in dialects of Fortran, ranging from Fortran 77 to the most modern Fortran we have. And the dimensionality of these stencils are from 1D to 6D. So here's a summary of our translation effectiveness. Overall, among our benchmark codes, we discovered 93 candidates. And of those candidates, 77 were translated using Sting, and 11 were failures. And of those failures, some of them were things that were doing things semantically that we couldn't handle, and others were timeouts. Now you'll notice that 77 plus 11 does not equal 93. There's an additional column here which is candidates that were not actually stencils, because our front end was thinking that this particular piece of code looks like a stencil, but it actually turned out to not be a stencil. If we look at the cumulative time distribution of the times to perform synthesis for this translation, the vast majority of them happen in just a matter of seconds or minutes, right? So at 50%, we're at about 100 seconds. On the right-hand side, you see that there are a few that take a very long time to synthesize. And that's because those stencils are high dimensionality. They usually consist of 3 dimensions with maybe 5 loops, and the size of the invariants there are up to 455 AST nodes, which is an order of magnitude larger than kind of the state of the art for general invariant construction. Now, the experiment we did to show speed up was that we translated these stencils to halide, and then we auto-tuned them on CPUs, on our Xeon CPU with 24 cores, and we also ran them on a Titan GPU with kind of just a naive GPU schedule, just doing the typical blocking you would do. So this chart is just showing the ones that are the most difficult problems, the ones that are, the hardest for us to synthesize, and we get speedups up to 17x here, and our median speedup was 4.1x, and the minimum speedup we got was 1.84x on 24 cores. So to talk a bit about related work, there's kind of 3 categories of related work. There's automatic invariant generation, and we see automatic invariant generation that could really help, as something that could really help us, because if we could get those invariants, then finding postconditions will be much easier. But the current state of the art, like I said, in automatic invariant generation is much smaller in terms of the size of invariants they can come up with. But of course, those invariants are much more general than the ones we're creating. In terms of compiler techniques, of course, there's the polyhedral model, which we think could really benefit from lifting. So if we get rid of all the hand optimizations and pass it to a polyhedral compiler, that could potentially have massive increases in performance. And finally, there's also other lifting strategies, and the big precursor is QBS, which was Alvin Chung's work, which did verified lifting of ORM code from Java. So to summarize, we demonstrated this system called Sting, which does verified lifting of stencil computations by synthesizing postconditions and loop invariants. Much of our effort was actually in figuring out how to generate sketches that could tractably generate postconditions of the form we require. And the performance results show that this strategy can lead to huge increases in performance, while also outputting code that is now much more maintainable and simpler to port to new architectures. Thank you.
Hi, Milan Kulkarni from Purdue University. Great work. So it seems obvious to me that, and you sort of mentioned this too, that as the dimensionality of the loops go up, that your synthesis time goes up. What about if you're going to higher order stencils? So as the complexity of the stencil gets
That's a great question. We actually found that the number of loops is going to be the biggest factor, but because we're doing this concrete symbolic evaluation to build those templates, that actually makes it so that higher order stencils are less of a problem for us, at least higher order in space. Higher order in time, of course, is going to be just as complicated.
Sure. Thanks.
Clemens Greik, University of Amsterdam. I'm a bit surprised you didn't find any example where the hand optimization was actually getting better results than your code generator.
I'm sorry, I couldn't hear the...
I try again. I'm a bit surprised. Seemingly, if I understand you correctly, you did not find a single case where the original hand optimization proved to be smarter or more performant than what your code generator achieved. Is that true?
That is the case for the benchmarks that we looked at, and one major reason for that is that a lot of these optimizations were done, in the early 90s, like when computers were much simpler, and that Fortran code lives on to today. And so, for example, one of our benchmarks was NASMG. And if you look at the NASMG code, it has this 2D loop inside the 3D loop, which is trying to pre-compute a bunch of things. But that actually doesn't help right now because we have so much computational power, and it actually increases the amount of memory traffic. So that's one of the reasons why we do better.
Aaron Su, Indiana University. It wasn't clear in your evaluation of the candidates how much the parsing is a bottleneck, or if it's a bottleneck at all. Were there cases where the parser wasn't able to successfully identify stencils that it should have been able to, and as this grows, are the number of false positives that the parser identifies going to become a problem, or how much of this is a parsing problem?
I see. So we were very careful to try to make the parser as non-strict as possible, while still leaving out many things that were obviously not going to work in our system. I think that our strategy in doing this is going to err generally on the side of marking things aggressively and then just trying it out, because the loss there is just time. And once you pay the time once, though, you can have that benefit forever and generate new versions of code from summaries. So it's worth throwing a bunch of time at it, even if it's a futile attempt.
I have a question as well. So you emphasized the synthesis parts, especially these post conditions. You didn't say much about the verification problem and how much time it takes as well. Can you elaborate on that?
Yeah, so we spent some time making sure that the form that we pass things into Z3 is a form that Z3 is pretty good at understanding, and all of our problems just take a matter of seconds in Z3. So we were able to get that down very, very low.
Was there any correlation between the way you achieved the synthesis and the time it took to verify?
Unfortunately not. The verifier and infrastructure within Sketch is very different from Z3, so they were actually quite different.